Rank in order from largest to smallest. Potential differences: delta voltage of C. C is for capacitor. For 1 through 4 of the 4 capacitors listed in figure 1, make the items equivalent, overlap them. So we want to go from largest to smallest of potential difference, potential being voltage. So the formula we're going to use is Q equals C. I'm going to write delta V, but sometimes you'll just see V for voltage. Same idea. Voltage is always a difference. So writing delta V is kind of redundant. I just like to do it anyway. All right. So what I have here is just the same equation, Q equals CV. That's just the equation I have memorized. Then I rewrote it in terms of delta V, difference in voltage, of charge Q over C, which is capacitance. So for this then, we're going to have for 1, that's going to be Q over C. 2 is going to be, and I don't have to change colors for this, I just want to, Q over 2C. 3 is going to be 2Q over 1C. And then 4 is going to be 2Q over 2C. So these are all going to be voltages, and this is going to be V, specifically V1. So rewriting these, I can see that light blue it is. This is going to be V1 over 2 because Q over C is V1. This is going to be 2V1, and this is going to be, the 2's cancel, and we get V1. So we get, this is largest to smallest, largest to smallest. So V3, because it's 2, is greater than V1, which is equal to V4, which is greater than V2. So that's how we would approach this one, just pretty much straight formula, and then put them in order. So not a big deal. All right. Next, the SI unit of capacitance is going to be a farad. This is actually kind of a important thing to get straight. So the formula you're going to use most often for capacitors is Q equals CV. I'll write a delta V there just so that to emphasize that it's a difference, but we all know what's going on. And you're going to hear a lot of names for these things, which makes it challenging. So voltage is measured in volts, which is convenient, but it's also referred to as potential. So whenever you see the phrase potential, what is the potential of such and such, you can basically replace the word potential, electric potential, with voltage. Capacitance is what we're saying. It's measured in farads. And Q is charge. And the thing that gets tricky about this is it's measured in, is it coulomb? It's measured in coulombs. Don't know if there's an extra U in it or not. But it uses C. So farads, the symbol for that is F. The symbol for charge is the coulombs, or the dimension, the unit, is coulomb, which uses the symbol C. So it's really easy to get the symbol for coulomb, which is for charge, confused with capacitance, which is C, but actually uses the unit farad. I know it sounds kind of convoluted. I'm sorry. I wish everything was as simple as voltages. Voltage, symbol V, stands for volts. It's not. But this is a little bit confusing, and it's good to have it really straight right away. So the SI unit for capacitance is farad. Capacitors are measured in farads. You'll usually see milli or microfarads. All right. A negative charge, if free, will tend to move towards. So this is a pretty reasonable concept here. So I'm going to go a little bit overboard in explaining it. the easiest way I think of it is parallel plate capacitor, because parallel plate capacitors, one of the cool things about them is they create, for the most part, a uniform field. And the way I create a parallel plate capacitor is I get two metal plates and I hook it up to a battery. And this is going to be some battery of voltage, I don't know, delta V. And so what this does is this battery creates a voltage difference, a V on the positive plate and a 0 on the negative plate. It doesn't really matter what you choose to be your voltage, because this only gives you a delta V. As long as the positive minus the negative is V, so like 9 volts and 0 volts, then it works. It could also be, just for craziness, 11 and 2. Let's say this is a 9 volt battery, 11 and 2, or this could be like, I don't know, 0 and negative 9. As long as the difference between the two is the difference of the battery. All right, so this is going to create an electric field. Electric fields are drawn from the positive charges to the negative, or positive goes out radially from electric fields go radially outward from positive, and electric fields go radially inward to negatives. And so what's going to happen is we're going to draw the electric fields from the positive charges to the negative. So we're going to get electric fields that look like this, from the positive to the negative. So now this is kind of the picture I use for anything that has like potential or electric fields. So if we want to draw the electric potential lines real quick, then they are going to be from the equally spaced within a parallel plate capacitor from the high voltage, which is V here. So like here, oh, that was a terrible line. Right in the middle, this would be V over 2. This would be like 3/4 V. And this would be like 1/4 V. So the idea is that you go from high voltage to low voltage, or from high potential to low potential. All right, so the concept is there. A negative charge, if free, will tend to move. I'm just going to cross out the toward infinity or away from infinity. Infinity is just a point, and it really means nothing. Like it's like saying it moves towards 3 meters. It's like, why? What's special about 3 meters? Nothing. It's just an arbitrary point. It's like, well, what about 6 inches? Why does it move towards 6 inches instead? Why is this? No. Infinity is just a point. No, doesn't make sense. That's like saying if you have gravity and a ball, and it's like, well, when you let go of a ball, it just naturally moves towards the earth. And it's like, that's not the reason why balls fall when dropped. It's because masses attract each other. Earth is a big mass, and so the ball is going to be attracted to the earth, not just to some abstract concept of down. So toward infinity doesn't make sense. From high potential to low potential. All right, so this, we're going to have a negative charge. I'm going to choose this negative charge to be an electron, just because it's convenient. And so if we put an electron right here, we can see that the electron is going to move this way. It's going to be repelled by the negative charges on the left plate, and it's going to be attracted to the positive charges on the right plate. So it's going to move from high potential to low potential? No, because this is high potential on the right, low potential on the left. It's going to move from low potential, which is away from the negatives, and towards the positives. So it's going to be this one right here. So, and then looking at this one just to make sure, in the direction of the electric field, no, it's going to specifically move in the opposite direction of the electric field. And in fact, these two answers are pretty much the same to each other. Moving from high potential to low potential is the same as moving in the direction of the electric field. So neither of these are going to be correct, and the fifth answer is going to be the correct one. So I know that's a lot of explanation for a relatively simple question, but it's really easy to get confused, and that's why I draw a picture like this pretty much every time I do this kind of question. All right, next one. Two protons are launched with the same speed from point 1 inside the parallel plate capacitor. Okay, I'm going to draw electric field lines real quick. Electric field line from positive, coming out of positive, going into negative, source and a sink of electric fields. Points 2 and 3 are the same distance from the negative plate. Okay? So is the change in potential energy, U is potential energy, of energy along path 1 and 2, larger than, smaller than or equal to blah, 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 match the word to the column, appropriate sentence. Okay, so one way to think of this is like a ball falling to earth. So if you think of this in terms of like gravity, this is high, I'll say potential energy. I know, energy written terribly, you get the idea. If there's a ball like that, and there's a ball like this, and they both start with the same speed, the velocities will be different because velocity includes direction, but the same speed, then which one's going to have the bigger change in potential energy when they get to a set distance h off the ground? So that's the same question we have here, except instead of having the ground, we have the negative plate. So in this picture up here with the ball, we have a force, gravity, pulling the balls down, and here we have a force, electric, pulling the charge towards the negative plate, the positive charge towards the negative plate. We also have a electric force from the positive plate pushing the positive charge away. You add together, you basically get one force. So if you think of this in terms of gravity, a lot of the intuitive sense that you get from physics 1 applies here. And so we're going to conservation of energy, energy kinetic initial plus energy potential initial equals energy kinetic final plus energy potential final. We can choose energy potential to be, we don't care about the energy potential per se as much as the change in energy potential. So energy potential final minus energy potential initial. I initially launched with the same speed, so the energy kinetic initial for both of these is the same. And therefore it asks us the change in potential energy along the path inside the parallel plate capacitor is, the change in potential energy along the path inside a parallel plate capacitor shown is directly proportional to the so I think it's going to be directly proportional to the distance component along the electric field between the initial and final points of the trajectory. That is the change in potential energy along path 1 to 2. The change in potential energy from 1 to 2 is equal to that along 1 to 3. So yes, delta U between these 2 points, change from 1 to 2 and 1 to 3 is going to be the same. Another way of saying this is that it's a conservative field, and more mathematical way of saying this is work equals integral f dot dx. The dot product means that only the displacement that has to do that's parallel, only the force that's parallel to this displacement is counted. So the force, in this case, force is going to equal QV, or Q times E, sorry. Force is going to be the charge times electric field. We have the same charge here, so the force is going to be proportional to the electric field. The force is going to be constant, so we can pull it out of the integral. And so this is just going to be F dot, I'm going to write this as delta X, where delta X is the displacement. So the work, change in energy, the change in potential energy here is going to be the force, where the force for both of these particles is going to be straight up. The displacement delta x for 1 to 2 is going to be straight up. And the delta x for 3, this will be, I'm going to call this delta x 1, 3, and I'll call this perpendicular because it's I know that looks like a B, it's supposed to be 1, 3. Perpendicular to the force. And this is going to be delta x 1, 3 parallel to the force. And so because of the whole idea of how dot products work, that part is 0. The perpendicular does not play any role in providing change in potential energy. And here you can see that the vectors delta x that's parallel to the force is the same. Long story short, the change in energy for both of these is equal. I know a lot of explanation for a relatively short problem, but the concept here is important. And if better you understand this now, the easier future problems are going to be. All right, this is the proton speed v2 at point 2 larger than, smaller than, or equal to v3. So the idea is if you think of this like as a ball falling, or the proton falling towards the negative, if we increase the energy, so its initial energy is from its kinetic energy, its motion, its speed, and the change in potential energy, delta U, the energy it gains is going to be the same for 2 and 3. Therefore, you have a certain amount of energy to start with. You add the same amount of energy to both of them, so that 2 and 3 then have the same amount of energy total. Therefore, energy kinetic, which in this case is going to be 1/2 mv squared, those are both going to be the same. So the velocity, since the masses of both of these particles are the same, the velocity squared are going to be the same. Therefore, the velocities will be the same. So the initial kinetic energies of the protons are equal as their initial velocities are equal. Correct. The changes in potential energy as well as kinetic energy of the protons are the same. Yep, the change in potential energy. Yep, that's what we just talked about. The final kinetic energy of the proton moving along path 1 to 2 is the same, equal to that of the proton moving from 1 to 3. This proton speed at 2 is also equal to the proton speed at point 3. So a lot of explanation, but the concept there is important and worth knowing. All right, so that now the electric potential in a parallel plate capacitor is proportional to blank, where S is the spinning plate. All right, so I'm going to come back up here to my picture of a parallel plate capacitor, which I take great pride in. Bring it down here just so I can use it. And so the idea for this one is the electric potential in a parallel plate capacitor is proportional to S, where S is the distance from the negative plate. Yep. And so the more formal way of saying this is electric potential is negative integral E dx. To get we want to find electric potential. Electric potential is voltage. So the voltage in a parallel plate capacitor is proportional to. So in this case, the electric field, and this is a dot product, is going to be constant, because that's one of the things about a parallel plate capacitor is you have a constant electric field. So this becomes E negative delta x. The integral of just delta x is just going to be delta x. So we get negative electric field delta x. And it's going to say the electric potential is proportional to S, whereas the distance from the negative plate, in this case, instead of using S, I used delta x, which is the same as S. So voltage is proportional. The proportional is E for electric field. And so voltage proportional to the electric field. And I guess there's a negative in there. I should have counted as well. But we're good with that. So S would be the answer for this one. So hope that helped. These are some kind of quick questions that really do a good job of explaining some of the concepts you need for more complicated, in-depth questions. Hope that helped. See you next time.